Okay, everybody. So last time, what did we talk about? Last time we talked about rigid bodies and kind of defining them. Also, yeah, that whole like little interlude about, not allowing reflections and stuff. I looked into this and like tried to find some references. Basically, all the references just say that like what we ended up kind of like discussing is like points have to be constant distance and it has to be orientation preserving, i.e. no reflections allowed. So there's not really, as far as I could see in the literature, there's not really a tighter definition in terms of the points on the body other than constant distance and no reflections allowed. It's basically, yeah, I don't know. There wasn't anything more satisfying than that, so that I could find in a quick look around. So sorry. If anyone has any better ones, let me know. Okay, so this, we talked about reference frames. And basically this idea that they can be attached to rigid bodies, and that's how we think about their attitude. We talked about attitude representations and basically surveyed all the common ones that you'll see. There are a few other ones that are weird, that are very uncommon. The ones we talked about that was a pretty exhaustive list. I feel like you'll probably not run into anything that wasn't on that list in practice. Then we talked a bunch about rotation matrices. And these are kind of the, I don't know, the mother of all rotation representations in some sense. They're like the most natural one and kind of the one that has the most, the least number of quirks, let's say. Okay, so today we're gonna take a little like diversion through linear systems to kind of catch us up on a few things that a few people maybe didn't see before, specifically with regard to the stability stuff we were talking about before and like eigenvalues and complex numbers and that kind of stuff. Then we're gonna take that stuff. That stuff actually slotted amazingly well into what I wanted to talk about today. So that was good. Then we're gonna take a little tour through some group theory. And then we're going to talk about sort of rotation matrix kinematics, i.e. how you sort of integrate a velocity, an angular velocity into a rotation matrix. Like how do you integrate a gyro, that kind of thing. And then if we have more time after that, we'll kind of keep the party going and talk about quaternions and some other stuff, which is kind of the next thing. Okay, so linear systems review, and this is going to focus really on linear time invariant systems, and this is not going to be exhaustive at all. It's going to be really quick, but hopefully, set some things straight, and maybe give you a little different flavor on things. So the simplest linear system that you can write down is maybe this scalar case in one dimension, which would be something like x dot equals ax, right? So this is a first order linear ordinary differential equation, which the goal here is to solve for x of t, right? And as everyone who took like a freshman or sophomore calc kind of class knows, the solution to this is x of t equals e to the at x naught. And this a, right, we're saying everything here is a scalar. This is a real number now. So given this is the solution, right, this is obvious. So I plug this back in, I take the derivative, I get a e to the at, and that's sort of a times x, right? Okay, so the kind of implications for what we talked about last time, right, is if a is positive, then e to the at goes to infinity as t increases, and this is unstable. And that's kind of, the story we had before. And then if a is negative, e to the at goes to 0, and we call this stable. So that's super simple. Everyone knows this. What we're going to do now is look at the complex scalar case. And this, I think most people have seen before as well. This is kind of a simple harmonic oscillator situation. So we're going to do the same thing but we're now going to look at x dot equals ax equals sort of, we're going to say b plus ic, where b is the real part and c is the imaginary part of a times x. And unsurprisingly, the solution is the same. It's just e to the at again, but now it's b plus cit times x naught, where this is now a complex exponential. And if we kind of pick that apart, we can say it's equal to e to the bt times cos ct plus I sine ct times x naught, right? So this comes from, this is added together up here. So this is the product of e to the bt times e to the ict. And then e to the ict, we can use the Euler identity that says that thing's equal to cos plus I sine, right? So no surprises there. Everyone's seen this from like undergrad calculus and stuff. Okay, so the stuff that we've been talking about before with eigenvalues and stability now, hopefully this is clear. This scalar complex case basically sums up the whole story of stability for n-dimensional systems with eigenvalues. The real part shows up in this exponential up here, and it's just like this, right? So there we know, basically we just have to pay attention to the real part. And the real part sort of, we're going to call this the envelope. And I'm going to draw this in a sec. Basically, this exponential kind of acts as an envelope for the wiggles coming from the complex part. And then this imaginary part, right, the stuff coming from the imaginary term, this gives us oscillations, wiggles. That's the way to think about it. So if I draw a few of these cases, I've got, so sort of like mimicking what we had before, we're going to have, say, the a greater than 0 case. This, what we have here, is the e to the bt term. You can think of this as sort of this envelope that looks like that exponential. And then the complex, the imaginary oscillating part kind of does this inside the envelope, right? That's how to think about it. And so basically the, oh, sorry, that should be e there. So again, you just have to look at the real part. You can kind of, that's what's happening with this envelope on the outside. And then the wiggles inside kind of from a stability perspective, you know, aren't telling us a whole lot. Okay, then we have the b less than equal to 0 case, same story. You've got this exponential envelope thing happening. So you have this thing decaying, and I should be consistent about the colors and stuff. So this guy is doing this, right? And sort of putting this bounding, decaying exponential envelope around the wiggles. Okay, so that's the stable case, right? And then the last case is this, you know, this sort of one we talked a bit about before that we called sort of, was inconclusive. This is sometimes called marginally stable. So if b equals 0, that term out front is just 1, does nothing, right? So the envelope is just constant. And so then it's just the wiggles. And those guys stay sort of bounded maybe in the linear case, right? Okay, so this is b equals 0. So that's the whole sort of like story about complex, you know, in the scalar case solution. So the takeaway message is the real part determines stability. And the imaginary part determines this oscillation frequency, right? Because that's showing up inside the sines and cosines, right? So C is basically omega, right? Okay, so that's that. And physically, right, this is basically a simple harmonic oscillator. And the real part corresponds to damping if it's negative. If it's positive, this corresponds to like negative damping or some kind of energy increase that's leading to blow up. Okay, so now we're going to kind of like connect this complex scalar case to like the general case. So I'm going to do that in kind of maybe a weird way. First, I want to look at, and this is going to like tie us into some of the group theory stuff we're going to talk about. So I want to look at some particular 2x2 matrices. I'm going to look at the following matrix that we're going to call J for now. And I'm probably going to be terrible and overload my notation later. Sorry. So, okay, so this guy J, what's J squared? Oh, come on. Someone can do this in their head by now. No? Minus I, right? So this is -1, -1. Cool. So this is minus I. Okay, so the fun now begins. This matrix J, algebraically, so J and the identity, if I take these two guys, they act exactly like 1 and I, the unit complex number. Does everyone see that? Basically, we have by definition, right, for complex numbers, I squared equals -1, right? Here we have J squared equals -I. So if I think about the complex numbers as vectors with a basis of 1 and I, right? And people have seen this before at the complex plane kind of idea. I can replace 1 and I with this identity matrix and this J matrix. You can think about these as the same basis vectors. And then I can do everything I do with complex numbers with these 2x2 matrices, and you'll get exactly the same answers. Who's seen this before? Only a couple of people. Okay, cool. Now we're into some fun stuff. All right, cool. So, so takeaway message, J and I act exactly like I and 1, aka complex numbers. Okay, so now, so the idea here is that, like, said differently, if I have some matrix, 2x2 matrix A that equals B times the identity plus C times J, this, and like the thing we wrote before, A equals B plus CI, these two guys will act exactly the same algebraically, right? Does anyone know what this is called? And I have two things like this that are like different representations that act the same way algebraically. Yeah, you got it. This is called an isomorphism. So we say that, this is fancy math speak, not super important, but we say that these 2x2 matrices are isomorphic to the complex numbers. It means they behave exactly the same way algebraically, and they're effectively interchangeable. We say these guys are isomorphic. And this basically means, you know, like functionally identical is the way to think about this. And this is a hint of things to come. Okay, so knowing this now, and knowing what we just talked about with the whole eigenvalue or complex exponential nonsense, what do you think the eigenvalues of these 2x2 matrices are? So this is now, if that matrix A is actually, right, if I expand it out, it's B minus C, C, B, right? So what do we think? These are isomorphic if they act the same way, blah, blah, blah. What do the eigenvalues of this have to be? Yeah, they're going to be the same as that complex number, right? That's B plus or minus CI. And you can figure this out easily enough, right, by solving a quadratic equation. And what do we think and also, right, who here has not seen the matrix exponential before? Everyone's, okay, so you haven't seen it. So, okay, so this will be good for at least some of us. So if I have this now, it's not super surprising that I can also do the following thing. E to the AT, I can take this A matrix and raise it, e to that thing, just like I did with the complex number. And I get exactly the same answer because they're the same thing, right? So this is going to be E to the BT times cos CT times identity plus sine CT times J. So this guy we call the matrix exponential. And then the rest of this is all the same, right? Okay, so this is basically just based on the argument that these guys, these two by two matrices are identical to the complex numbers. I can plug them in everywhere I did the complex number things and it all works, right? So therefore this all kind of works. This thing should work, right? That's sort of hand wavy. So the sort of like more general story here is that I sort of showed you that complex exponentially thing by analogy. The general story is for any equation like of the form x dot equals ax, where x is any, a vector in Rn, so n dimensional. We have, the same story where x of t equals e to the at x naught, just like the scalar case, but now this e to the at thing, it's a matrix exponential. And we have to define this somehow, right, to compute it. And there's a few ways to do this. The simplest thing is literally what we do is, everyone knows the Taylor expansion for e to the at, the exponential function. We just plug the matrix into that definition. So formally, we could formally define e to the at by the power series. So we've got e to the at equals sum from n equals 0 to infinity of 1. I guess I should do it this way. This is a to the n, t to the n over n factorial, right? And the first two terms of that are going to be identity, at, 1/2 a squared t squared, 1/6 a cubed t cubed, etc. Cool. Okay. So most of you have seen this before. Quick interlude. Does anyone know how we actually compute matrix exponentials in a computer? Like if you actually had to calculate this thing, how would you do it? I just gave you this power series definition. So theoretically, you could just do that, right? I could just take that power series out to a ton of terms until I get to like, full machine precision. That's not how it actually gets done in the computer because you start to get round off errors and stuff accumulating. So it's not great. Yeah. So that we're going to talk about in a second. It turns out that doesn't work in general because you can have cases where A is nilpotent, doesn't have a full spectrum of eigenvalues, blah, blah, blah. So you can't do a nice decomposition on it. So it doesn't work in general. Anyone have any other ideas? Yeah.
Is it Haley Hamilton?
Nope. Yep.
Diagonalize?
So that was the same thing that we kind of just talked about. In general, you can't do that, right? So if you have like, if you have a singular matrix, right, stuff like this, without a full nice orthogonal eigenbasis, you can't do that, right? Yeah.
Can you do upper triangular or lower triangular?
It doesn't really help you. Yeah. Okay, so there's a magic trick you can play. This is just a fun fact. The trick you use is something called scaling and squaring. So if I chop the matrix A in half and take that guy's exponential, right, the solution is actually like A, so 1/2, if I do like e to the 1/2 A, right? This guy squared equals e to the A, right? You see that? So what I do is I actually just chop A in half a bunch of times till it's really small. And then the Taylor series is really accurate with only a few terms. So I chop A in half a whole bunch of times till it's below some threshold size. Then I plug it into some Taylor expansion that's accurate with only a few things, and then I square it a bunch of times after that to get it back. So this is like this really clever little trick that you can use. And it turns out you don't use a Taylor expansion either. You use a Cadet approximant, which is a little better than a Taylor expansion for a few reasons. Anyway, just a fun little thing since we're doing numerical things. Okay, so now we are going to do the eigen decomposition thing, which you can't do in general, but it's sort of revealing. Yeah. If you, sorry, say it again. Yeah. As what? As if you just try to like store it as like a series. Oh, as a series expansion? It's probably pretty similar, but it turns out the scaling and squaring trick is numerically a lot better than the Taylor series trick. So you basically you might be giving off some sort of box for basically accuracy. Yeah. So the scaling and squaring trick, you can get it to machine precision. And the Taylor series trick, you start to get like small divisor kind of issues in the series, and you start to get numerical round off kind of errors pretty quickly as you take that out to a bunch of terms. If A is small though, and you're just trying to do this quickly on a computer for your own purposes, you can use the Taylor series, out to a few terms. That's fine. Okay, so here we're gonna just say, okay, so assuming we do have a nice diagonalization of A, like eigen decomposition, right? Assuming a nice eigen decomposition, which is not, true in general, I can easily write down A's that do not have a nice eigen decomposition. I can plug that into e to the AT. This is going to be I plus, now we got the eigen decomposition, just A. Sorry, I messed this up. And then the next term, let's see what happens with the next term. So we're going to get the 1/2, and then we're going to get V d V inverse, V d V inverse. The V V inverse thing in the middle cancels out. So we just get V d squared V inverse, right? And that sort of thing with the V's canceling in the middle keeps happening so that the higher order terms turn into just like V d cubed V inverse t cubed. This has got a t squared plus ... such that basically what's happening here, right? The diagonal matrices are getting exponentiated. The V's on the sides, you can pull out of the series, right? So that means this whole thing is just equal to V e to the d V inverse. So now what does this tell us? In terms of like the complex story. So this diagonal matrix now, that's just a whole bunch of the scalar complex case on the diagonal. It's all decoupled. So I'm back to exactly this scalar complex case that we talked about right out the gate, where it's a simple harmonic oscillator it's got a complex envelope that's either growing, shrinking, whatever. So any n-dimensional system, if I can take an eigen decomposition in that eigen basis, it's just a whole bunch of those scalar cases. So basically what I've done is transformed it into just a whole bunch of that scalar complex case, the 1D case. I can look at those real parts, decide stability, blah, blah, blah. And that's where we were talking about stability last time, right? Okay, so let's write that down. In eigenbasis, system decouples into lots of simple harmonic oscillators, basically. And it's just simple harmonic oscillators along each of these V directions, basically, right? And so really the eigenvalues, as in the scalar complex case, tell us the whole story about stability. The V's are just telling us like sort of how this thing's oriented, right? And which directions these things are happening in. Okay, any questions about that stuff? That was a very, very quick, hopefully, review for everybody. Yeah.
So when you can't do the eigenvalue composition, you can always get a Jordan form. It's like,
yeah,
like the individual like Jordan blocks related to like the minimal component
Yeah, so there's a bunch of ways to look at this. Basically, the Jordan blocks end up being this 2x2 case, in most cases, and they correspond to. So if you've ever done this, in a class where you do the scalar case, it corresponds to having repeated eigenvalues, and what you end up getting is a t that shows up, right? You have to like guess another type of solution, and really, what's going on? The Jordan blocks, the ones in the off diagonal, are basically the t's that show up in the scalar case. It's all the same stuff. I don't know a better way to say it. Does that sort of answer the question, I guess?
Yeah, I was wondering if it's like I said, interpreted like a physical intuition for the system I'm dealing with.
Yeah, I mean, repeated eigenvalues. Let's see, what's the other kind of way to think about this? It corresponds to nilpotent A matrices also. So it corresponds to like a rank deficiency in the A matrix. The simplest version of this is that if you write down a double integrator, it's 0, 1, 0, 0, right? In the A matrix, and then like whatever the control input. So if you take e to the AT there, what ends up happening, you can't take an eigen decomposition, but you can take the power series, and A, because it's nilpotent, turns into a 0 matrix really fast, right? Like after one term. And that's so the exponential still works. And you pick up a t in there. And that thing is a Jordan form, right? That A matrix where it's 0, 1, 0, 0, that's the Jordan form, right? It doesn't have a good eigen decomposition. That's it. Corresponds to something like an integrator, actually. So physically, yeah, those nilpotent cases, I would think of them rather than simple harmonic oscillators as integrators. So in the 2x2 case, it's a double integrator system, constant velocity, where it's a t ramp, right, rather than exponential. That's my best off the cuff explanation. Anybody else? Okay, cruising along. Okay, so next up, we're going to do some group theory stuff. This is fun. And it's sort of fortuitously connected to this whole linear system story. Okay, so who knows what a group is? Yeah, go.
I like a set with associated operations.
Yeah, that's pretty good. So let's start writing this down. So we'll say a group of elements set, whatever. A group of elements with a bunch of things that you just said. So first one is it has a multiplication operation. It has a couple of things. Anyone else? So you said multiplication and closed. Cool, we got that. There's two other things you need. Yeah.
An identity and a null.
It's got an identity. It has a null element, sure. And it has one other thing though that's important. It has an inverse. Yeah. So it has an identity. It has an inverse. Okay, and then the final thing is and it's closed. Group balance with these three things that is closed under multiplication. And what do I mean by that? Yeah. Exactly, yeah. So I take any two things from this collection of things, I multiply them together with the multiplication operation, I'm guaranteed to get something that's in the group, right? Okay. Cool. Okay, so examples of these things. Let's do it. Who's got some? There's some easy ones. I'll kick it off with a really easy one. Positive real numbers. Under standard multiplication, what's the identity? What's the inverse? Reciprocal, right? 1 over that number. Okay. How about some other ones? That seems likely. It's a weird one though. Yeah. Cool. Other ones? Sorry? Yeah, we're gonna get to that one. That's why we're doing this. So another like simple one is the integers. What's the multiplication operation there? Sorry?
Addition.
Scalar addition. Yeah, is the multiplication operation there. So it's sort of an abstract notion of multiplication, right? Okay, another one that is maybe obvious now is complex numbers, what we just talked about under standard complex multiplication. Anyone else have any other good ones before I start rattling off some other weirder ones?
Square matrices.
Square matrices, not just square matrices though. Remember these properties. So what does it have to be?
Non-zero.
Not non-zero. For an invertible, right? Yeah, same thing. So the set of all invertible n by n matrices for a given n, do you know what that's called? It's called the general linear group, or GLN. Okay, that's a good one. Any other ones? Okay, I'll start giving you some fun ones. So there's all kinds of discrete groups, discrete symmetry groups. So a simple one would be C4, also called the cyclic group with 4 elements, which is the symmetry group of the square in the plane. So it's a set of all sort of plane rotations that leaves a square unchanged. So like 0 rotation, 90 rotation, 180 rotation, 270 rotation. So if I wrote those down as rotation matrices, right, and I multiply any of those together, I get another one of them, right? So that's closed, and it's a discrete group with only a finite number of elements, 4 elements, right? So this is kind of the rotation group of the square. Just fun. Let's see. Okay, so then the ones we care about for our purposes, rotations of Rn, which are called SON. I'm going to say what that means in a second. And that's a subgroup of GLN, right? It's just a set of particular matrices that's closed, where if I multiply any 2 of them, I get another one. Turns out pretty much all the groups we care about are just particular classes of matrices where they form a closed set. So they're in general sort of subgroups of this GLN, pretty much all of them. Another one that's really good are rigid body transformations, which we're going to talk about too. Anyone know what that one's called? SE3, so for special Euclidean group. And this is translation and rotation together, right? Okay, so some more stuff. So these are some good examples to just kind of like get some ideas flowing. Some notes on these things. So number one is, practically speaking, every group you will ever need or care about is just a matrix group. They all have matrix representations. You can make up weird ones that do not have matrix representations. How you do that is you make up infinite dimensional groups. So the formal thing is any finite dimensional group has a matrix representation. So those are all the useful ones. So I'll say useful groups are really just matrices, particular matrices. And kind of what this is trying to get at is formalizing and generalizing the idea we just saw with the complex numbers. So with complex numbers, I've got this, 1I sort of basis representation. I have this like identity matrix, J matrix representation. They act exactly the same way algebraically. They do all the same things. I can plug them both into power series and get the same answers. I got exponentials. I can define trig functions for them, whatever. They do all the same stuff, but like I write them down differently, and they can act differently numerically in a computer maybe, but they're kind of underlying, they're the same thing, right? So this group concept, what it's really trying to do is abstract that notion of like separate this notion of representation for what the underlying like mathematical object is. So complex numbers do what complex numbers do. I can write them down with ones and i's or identity and J matrices, but they act the same way and they're really under the hood the same thing. That's what this is trying to get at, right? So there's lots of ways to write something down, but if they sort of do the same thing, they have to sort of like algebraically act the same way, right? No matter what. So that's kind of like what this is all about. So it's trying to separate this idea of representation from like underlying structure. So we'd say, you know, both of those that set of 2x2 matrices is just a matrix representation of that group, right? That makes sense? Or you can have the complex number representation. They do the same thing. Okay, so that's fun. So now we're going to sort of a couple more definitions. So continuous groups, where you can think of them as like having an infinite number of elements and they're smooth in some sense, and you can take derivatives maybe and do calculus with things, kind of smooth continuous groups as opposed to discrete groups. So which of these are discrete that I just wrote down? The square one, C4, also the integers, right, are discrete. So I can have continuous and discrete groups. Continuous groups are special. So these would be the rotations, right, SE3, positive reals, those are all continuous, as opposed to discrete like the integers and C4. These are called Lie groups, L-I-E, after this guy, Sophus Lie. It's pronounced Lie, not lie. I'll call Lie groups. And these are super useful in lots of robotics contexts. And 3D rotations, like we've seen. This is SO3. Who knows what the letters stand for? Special orthogonal, right? So special means special and 3D, right? And this special, so orthogonal, we know what that means. This is the Q transpose Q equals identity thing. And then special is determinant 1. So this is the stuff we learned about last time with rotation matrices, right? Okay. And then this is, you know, self-evident. Okay, this is a crash course. We're going to do a little more of this, but this is sort of the intro. It's mostly just vocabulary and stuff, and sort of generalizing this sort of ideas we saw with rotation matrices. Questions about any of that? Okay, yeah.
So like, when you have like a non-linear, so when you say the matrix, can you not have like a non-linear group?
So what do you mean by non-linear, I guess?
Like, I guess an operation like different operation that's non-linear.
So I mean, in really, all of this stuff is nonlinear. So like if I think about rotation matrices, they don't commute, order matters, and they're not sort of they're not a vector space. Like, you know, like I can do roll, pitch, I end up here, I can do pitch, roll, I end up totally different place. So they're weirder, they're quite weird. They're not vectors, they don't add like vectors. And most of the things we sort of know about them, they're not linear in a very deep sense that we're going to get into in a second. So I would say these are not linear things. That's sort of, they have matrix representations. I can write them down as matrices, but pretty much everything about them is not linear. It might not be super clear right now because we're used to thinking about matrices as these like linear transformation kind of objects, but these are not linear things. There's geometry under the hood here that's going to be interesting and fun that we'll do a little bit about. But yeah, like this Lie group notion, these are continuous sort of, you can think about them as smooth, right, in some sense. So one way to think about these things is like, so the set of set of n by n matrices is a vector space, right? I can just stack the columns in a big vector and think about it as Rn squared, right? So GLN is sort of a vector space, right? SON, though, is some restricted subset of that vector space, right? With a bunch of constraints on the elements. And in general, those constraints can be arbitrary and nonlinear. And in fact, this one is nonlinear, right? It's a quadratic constraint. So the geometry associated with these things is nonlinear. And you can think about it as like, if I imagine the set of all possible Q matrices here, as just n by n matrices, that's a vector space. But then to be in SO3, it has to obey these two nonlinear constraints, right? So actually the set of those matrices forms this kind of weird submanifold, like weird curved surface in this vector space. So it's totally nonlinear and everything about it's nonlinear. Aside, yeah.
Another question. Can we generalize the fact that rotations are in as a group? Can we generalize that for different attitude representation? So does that necessarily imply that the Quaternion is also?
Yeah. In fact, it's a group representation. It's just another representation of SO3, right? Quaternions are a little weirder. They're not quite. We're going to get to that like probably next time. But yeah, so the whole message here is there's groups, which are things that act a certain way. And there's representations of the group, which are just ways we write them down. So that whole story about attitude representations, those are just representations of SO3, right? So they're all just ways of writing down the same thing, and they should sort of behave the same way in some sense. That makes sense?
So basically, then kind of the goal of these different attitude representations, finding that quote unquote best way of representing.
Yeah, sort of. And best is all relative, right? Sort of best with respect to certain goals and certain, things you're trying to do. It's best for the task at hand, basically, right? Okay. Good. Okay, we'll keep trucking. So now let's see how we doing time-wise. We got some time. Okay, so now we're going to switch gears back. Well, not switch gears, but like continue on this trek through things that hopefully will make sense eventually. Rotation matrix. I'm going to dig into this rotation matrix stuff a little bit more. This is sort of, it is group theory, but we're going to do it in sort of a more intuitive way. So the question here is, if I have a gyro that gives me omega of t, like my angular rate that I measure, how do I integrate that into, say I know what Q naught is at t0, say I know my initial attitude, and I have a gyro strapped onto my thing, and I'm moving around, how do I integrate the gyro? To know what, Q of sort of t at some future time is. So how do I integrate omega of t from a gyro? Super practical question. So I've got this thing coming from the gyro, say I know Q naught, right? What I really need here is I need to go from omega to like Q dot of t so that I can like integrate this up into Q of t at some later time, right? And so the mapping from Q dot to Q is obvious. That's just like sort of normal ODE stuff, but the mapping between omega and Q dot is what we're after here. That's a question mark, right? I don't really know how to do that. It's not obvious. This is like a 3x3 matrix. This is a 3-dimensional vector. There's some weird thing going on in the middle there, right? Okay, so how do we do this? So the way we're going to get at this is first by thinking about velocities in a rotating reference frame. And my favorite way of sort of thinking about this is, say we have our inertial frame here. So these would be our n vectors, so like n1, n2, and 3. And I'm going to think about a record player spinning around, turntable, with an ant crawling on the record. That's the picture in your head. So we're going to have like this turntable thing. We're going to have some omega, say, that's pointing in the z direction for arbitrary reasons. And then I'm going to imagine I have these body vectors here, like B1, B2, and then I got my ant over here, DJ ant. And this is like the spinning. Okay, so this, I think I'm just gonna write these down. You'll have to like, if you stare at this for a little while, and I'm sure most of you have seen things like this before, you can kind of arrive at the following two things. So let's say the ant's position in the body frame. We've got X as the ant's position, and X in the inertial frame, the ant's position in the inertial frame. We got like these two things, right? The body frame position and the inertial frame position. So just the position with respect to these two sets of basis vectors. And I'm gonna just go ahead and write it down. Okay, so basically this guy is our rotation matrix Q times the body frame. And if I stare at this a little bit, so this is kind of obvious, right? I rotate this guy into the inertial frame. That makes sense. But I'm going to pick up a new term on the velocity due to the rotation, right? So it's not just rotating the velocity vector. You get an added term, which is omega cross. So omega b cross xb. And this is just kind of the usual thing. So if this is x, this is omega. I'm spinning, so I get like this extra velocity component due to the spinning, right? Everyone's seen this before? Cool. Has anyone seen this thing written down like this before? Sort of, kind of. Probably seen it without the Q on there, I'm guessing. This is sometimes called the kinematic transport theorem or something like that, but usually people write it down sort of wrong, in my opinion. So this guy, then, if I flip this around, I can invert it, right? And I can also write it as Q transpose x dot n minus omega b cross xb. Okay, so yeah, maybe kinematic transport theorem. Usually people leave out the Q's. Which is sort of not right. Okay, so now what we're going to do is think about a vector fixed in the body frame. So assume the ant's not moving. So we're going to get xn equals qxb. And then I'm going to take the derivative of this guy. X dot n is going to be q dot xb plus qx dot b, just the product rule. And because we said it's fixed in the body frame, this guy's zero, not moving in the body frame, right? So this goes away, and I'm left with just this term, right? So this kind of makes sense, right? It's derivative of the rotation matrix. Okay, so now what I'm going to do, so I have this expression for x dot n, and I have that expression up there for x dot n. So I'm just going to set those two expressions equal to each other. So I get x dot n equals q omega b cross x b. And remember that x dot b is 0, right? I'm going to set this guy equal to q dot x b. So this basically gives me the magic formula to figure out what q dot is. And I'm going to write it down like this. Q dot equals q times this thing we're going to call omega hat. So this is, you've probably seen this written down before, maybe in various ways. This thing is, I'll write it down, I'll just like define it. So this thing is defined such that omega hat times x equals omega cross x. It's just a matrix sort of version of writing down a cross product with a vector. So I take this like omega cross x and I try to like turn this into a matrix equation and pull this omega out. So it's some matrix times x. This is that matrix. That's all it is. Okay. So is this all kind of, yeah.
What are those numbers, the subscript numbers?
Oh, those are the elements of the vector omega.
Oh, I just can't read.
Oh, sorry. Yeah, my bad. 3, 2, 1.
Thank you.
Yeah, and it's skew symmetric. So that means omega hat transpose equals minus omega hat. And that comes from the skew symmetry of the cross product. So with the cross product, right, omega cross x is minus x cross omega. Yeah.
You can find it as a transpose.
I screwed up. Yeah, I did this before. The minus signs are in the wrong spots. That's what happens when I do this late at night without thinking enough. So this should be minus, minus, minus. Yeah?
Yeah.
Thanks. Okay, cool. Oh, and then we're going to call this thing with the hat. We're going to call this the hat map. So it takes a 3D vector and turns it into a 3x3 skew symmetric matrix that like is equivalent to the cross product. Everyone good with this? Who's seen this before? Pretty much everybody. Okay, cool. Who's seen this thing before? This like ODE for Q dot. Fewer people. So you've seen the cross product thing. Now you've seen the rotation matrix kinematic stuff. Okay, so here's some fun connections with what we just talked about with linear systems. This Q dot equals Q omega hat thing is a linear first order ODE. So we've got, again, Q dot equals Q omega hat. So if omega hat, say omega is constant, if omega is constant, this thing looks just like x dot equals ax, where the a is the omega hat now, right? So it's like a matrix version of this thing. So for constant omega, what is Q of t? Q of t, based on our whole discussion about linear systems, is going to be some Q naught e to the omega hat t, where this e to the omega hat t thing is just the matrix exponential we just saw. And Q naught's your initial attitude, blah, blah, blah. Yeah, there's some weirdness here in the ordering because, you know, for matrices that don't commute, the order matters, right? So here I might have written, you know, e to the at x naught. Here, because the a shows up on the right, the exponential has to go on the right of the Q naught. Does that make sense? I can define it the other way if I want to, but that corresponds to writing omega in the inertial frame instead of the body frame. There's some weird stuff there. Okay, any questions about this? So, okay. So next up, let's see. So for small delta t, just as like an aside, this thing is just a matrix exponential. We've got e to the omega hat delta t equals, or is approximately, if I just truncate the Taylor expansion, I get I plus omega hat delta t, which means if I have a vector x, e to the omega hat delta t times x is approximately x plus delta t times omega cross x. So intuitively, what this is saying, if I have some omega for some little amount of time or some small rotation, basically cross products are like sort of this like infinitesimal rotation kind of thing. So if I like have some omega for a little time, what it's what that rotation is doing is really kind of like giving me the original vector, and the modification is for small time is omega cross x. This is kind of a fun thing. Okay, and this thing, this omega delta t thing. So like think about an omega times a little time increment. So if I integrate omega just straight up for a little bit of time, we call this an axis angle vector, which we kind of talked about last time. And we're going to sort of write this, we're going to use phi to represent axis angle vectors. And this is basically axis of rotation times angle of rotation, right? So axis of rotation is a unit vector times angle of rotation in radians, gets you this kind of thing. And this whole like ODE business up here with this matrix exponential, what this is kind of telling you is that in general, the exponential maps you from axis angle vectors to rotation matrices. This turns out to be super, super useful in a whole bunch of contexts. One good example of this is, say I want to sample random rotations in like a Monte Carlo simulation or something like this. How do I sample random rotation matrices? It's pretty hard to like define a Gaussian over rotation matrices. So what I can do is just write down a Gaussian in R3, use it to generate random axis angle vectors, and then exponentiate them like this, and I'll get random rotation matrices with some mean, I can make it have mean whatever I want, covariance whatever I want, and I can generate nice random rotation matrices. And that's actually the legit way to do that if you want to sample rotations or something like this. And there's a whole bunch of other good things about this that are nice. E.g., Gaussian noise on rotations, that kind of thing. What else can we say about this? In general, there's a whole bunch of things this is good for, because it lets you kind of bootstrap things on rotation matrices via things you know how to do on vectors, right? So now I have this axis angle vector thing. I can do anything I can do with vectors, and I just exponentiate it, and I get rotation matrices, right? So it's good for a lot of things like that. Also, fun fact, unsurprisingly, you can also go the other way. So you can also define a matrix logarithm. So you can have Q equals e to the, say, phi hat. And then we've got phi hat equals log Q. And these are just appropriately defined matrix versions, which are in Julia, MATLAB, et cetera. In MATLAB, they're called EXPM log M. In Julia, they're just overloaded. So they're just EXP and log. Okay, cool. Any questions about this stuff? Yeah.
Does the mapping, does the exponential, like the mapping only holds for small delta t?
Sorry, say it again?
Does it matter how big delta t is when you're talking about exponential map from axis angle to rotation?
So not for the exponential. The exponential is well defined for all t. The log has some issues. The log has some branching and weird stuff. Actually, just like the complex logarithm does. Yeah. Have you seen these things called? We call this complex analysis. It's like you can have multiple sheets or whatever. There's like, basically it's defined like modulo 2 pi kind of thing, right? There's some weird stuff where you cross 2 pi, and you can think about this a few ways. It's sort of like another topic. But yeah, the log has some weird stuff, sort of mod 2 pi, wraparound flavored weird stuff. The exponential is always good. Okay, anything else? Yeah.
So what you were saying about like mapping the probability distribution on omega delta t to rotation matrices?
Yeah.
There's no issues in the fact that you can have multiple axis angles represent the same rotation?
So that does get a little weird, and there are some technical kind of additional things you got to worry about. So technically speaking, yeah, if you allow axis angles to be arbitrary, They wrap around it at, plus minus pi or 0 to 2 pi or whatever. And so if you have a Gaussian, say, which has non-compact support, meaning it goes out to infinity with non-zero probability mass, technically what you're getting if you do this is you're taking the tails of the Gaussian and they're wrapping back around, right? So you're getting more probability mass than you should and stuff like this. So there are some technical weird things going on, but if the covariance is small, the probability in the tails that's wrapping around is really small, right? So you're kind of okay doing it, basically, is the message. So yeah, there are some quirks, but practically speaking, this is like the right thing to do on a computer if you need to sample rotations, and you don't generally worry about the tails with like vanishingly small probability. If your covariance is like, pi, then you might have, then it gets weird. If your covariance is reasonable, like 5, 10, 15, 20 degrees, something like that, like practically speaking, what you would see in a robotics application, it's totally fine. Okay, yeah.
So you started the motivation by saying we're integrating gyro. So
Sorry, yeah.
You started the motivation by saying we're going to integrate gyro.
Yep.
But my understanding there is that there are two problems. One, you have the integration delta t has to be really tiny, and noise is a big problem.
So yeah, noise is always a problem. I mean, that's not going anywhere. But like, say we had a pretty good gyro that was pretty low noise. Turns out actually gyros are extremely good if you spend some money on them. They have very, very low noise. They have bias, which is a different thing. But their noise in terms of like angle random walk and stuff, if you get a good gyro, a high-end like ring laser gyro or something, they're fantastically good. So you can really just plug into this ODE. I mean, yeah, you can take a modulo. So you would do this with some kind of filtering, right? And like some fancier stuff, but assuming you had a really clean gyro signal, you literally would plug into like Q dot equals Q omega hat. You'd plug the omega from the gyro right into that. You'd start with Q equals Q naught, your initial attitude, and just integrate. Yeah, that would do it.
So you wouldn't be trying to like adapt step on the delta here, like straight to the
So I mean, adaptive step on the delta t, if I just write that thing down and plug into like an adaptive Runge-Kutta method or whatever, that's it. Sample rate is kind of a different issue, right? Like I can sample this, however finely I need to. I can do all kinds of things there, but like in principle, that's the continuous ODE that you want to use, right? I don't know if that answered the question or not.
Yeah, I was trying to figure out how you pick a small delta t or something like that.
Yeah, so practically speaking, I think there's the mathematically where it gets bad is it's really related to Nyquist sampling. So you think about this as like, sine, cosine, oscillating stuff, rotation stuff. You need to sample densely compared to the period of oscillation. So if this thing's wrapping around, it depends on the rotation rate, basically. But from Nyquist, you need to sample at least a couple times per rotation period, right? So that's kind of really what it comes down to. Practically, you want to go a lot faster than that, right? And practically, in a strapped-down inertial navigation system with a thing like this, you're sampling at like 100 hertz plus, and that's plenty. So it's not really practically an issue hitting the sample rates, I would say, most of the time. Like decent gyros can sample at hundreds of hertz, kilohertz even, and you're not going to spin faster than that on any real rigid body system. So I don't think the sample rate's typically a problem. Noise and bias and all that other stuff are problems, but that sort of gets dealt with in some kind of Kalman filter or whatever, right? But the core idea, this thing is sort of ports into the Kalman filter setup pretty cleanly. Okay. Okay, so then I'm going to just write down some more. We're going to sort of go back to our group theory interlude. Just finish that discussion off, and then we'll call it a day. So, so clearly there's something kind of special about this connection between axis angle vectors and rotation matrices, right? There's something going on here that's kind of special. And these kind of axis angle vectors or sort of corresponding skew symmetric matrices via that hat map. These are sort of, they're connected in a deep way. They're sort of velocities, right? They're something, so if we think about this in group theory terms, they are something called the Lie algebra. And this is written lowercase SO3, corresponding to the group. big SO3. So as I know, this is the algebra is denoted lowercase. I don't know. This is just definitions and notation. It's not deep. And this is called the Lie algebra as opposed to the Lie group. Who's heard of this before? Handful. Okay. Let's see. So kind of a few ways of looking at this from the Taylor expansion of the exponential. Again, you get this thing where, you know, e to the omega hat t is approximately I plus omega hat t plus higher order terms, blah, blah, blah. So in some deep sense, this Lie algebra thing is the linearization of the group. It's the linear term in the Taylor expansion of this rotation matrix, right? This is a rotation matrix. This is the Taylor expansion. This thing, this omega hat thing, skew symmetric matrix, isomorphic to vectors in R3. That's isomorphism again. Showing up here, it's saying that really this thing, right, it's about the identity, sort of at the identity. The Lie algebra is the linearization of the group in some sense. And in this sense of, in like a geometric sense, remember we talked about how you can think about this as like a submanifold with those constraints, like the determinant equals 1, Q transpose Q equals I. These are like equality constraints that define some submanifold, right? So you can think of like the space of rotation matrices as some surface, some like hypersurface submanifold. And at the identity on this curved manifold, this is the tangent plane, right? That's what this kind of thing is sort of doing geometrically. So then kind of the real reason this is cool and useful is we talked about how the group is nonlinear, non-commutative, all this bad stuff. It's not a vector space. The Lie algebra is a vector space. So this means you can basically port all your vector space tricks, everything you know how to do with vectors, sampling, adding, blah, blah, blah. You can basically do all that stuff on the Lie algebra and then sort of lift it onto the group via the exponential. So it lets you apply all the algorithms you know for vectors to rotation matrices. This is like a really, really useful trick that shows up all over the place. And especially in control and estimation, like doing Kalman filtering, you basically do this. You do it on the Lie algebra and then lift it. Okay. And we will do more of this sort of thing. Okay, I think that's good for today. Questions, comments, thoughts? We're done. Catch you Thursday. We're at time, right? I did that right. Yeah, cool. Okay, so yeah, I'm trying to gauge the room a lot here, if that has been clear, because like some people have seen a lot of this and some people have seen none of this. So trying to strike a balance there. If you're like lost on any of this, come talk to me for sure. And if this is boring, also let me know. And I'll actually I'm going to set up a like anonymous comment thing on Google Forms to try to help with this. Yeah.
Just as a reminder, your class is at 10 to 1:30.
Oh really? Did I screw that up again? How do I keep doing that? Yeah, I don't know why I keep getting that in my head. Okay, great. Then we have some more time. Thank you for being honest and like, you know, tolerating listening to me some more. Okay, that was a lot. That was a natural stopping place. So I just felt like, you know, okay, so we're gonna, yeah, I'll tease the next topic. So we did all this rotation matrix stuff. We talked a lot about group theory, Lie groups, blah, blah, blah. Where are we going with this? Okay, so We're going to next talk about quaternions. And I'll tease some fun things today, and then we'll do the meat next time. So basically, quaternions are super useful. Probably who's used quaternions before? Show of hands. Pretty much everybody. Awesome. So they're basically the standard rotation representation in anytime you need to do things numerically involving dynamics, simulation, computer graphics. They're kind of the standard way to go in a computer. So you got to kind of know about them. And we're going to make you do this on the next homework. They have no singularities like rotation matrices, which is good. And they also have fewer elements. They're more compact, more efficient, easier to deal with in a bunch of ways because you don't have to worry about so many constraints. So these are kind of why they're popular. Okay, so now we're going to do some geometry. And yeah, keep in mind that whole group theory idea, right? So these are another representation. They do the same thing. That's kind of the group theory idea. So what I want you to think about right now are the set of all possible axis angle vectors. And when I say all possible, I mean not allowing for repeating them. So geometrically, what I'm going to do, right, is I'm going to restrict the norm of this guy to be between minus pi and pi. So this is, not letting us have any repeats. So what is this as a set in R3 geometrically? Not hard. See, yeah, you're doing the hands. This is good. Yeah. Yeah, it's a ball in R3, right? It's a ball of radius pi. And when I say ball, I mean solid filled in ball, not the sphere, which is the hollow shell. Yeah. I'm intentionally not including the surface on one side, I guess. But yeah, we can do that if you want. Yeah, it is.
The normal with positive.
Sorry?
Normal with positive to the equality on the left-hand side.
Oh yeah, what am I doing? This is dumb. There you go. Thank you. Again, this was like 2 a.m. Apologies for the sleep deprived. Definitely let me know when I screw stupid things up like that. Okay, cool. So what we're going to do, this is a ball in R3. We're going to visualize this in 2D as a disk. So radius pi. Cool. So far, so good. So what happens if I'm like cruising along, say, integrating my gyro, say start here, cool, rotate, rotate, rotate. I get to here. Again, using this compact representation, what happens when I get to pi, and if I need to keep going, I have a discontinuous jump and I pop out over here, right? There's this kind of weird discontinuity wraparound situation, right? Basically, right, like if I'm at pi plus epsilon here, I end up at minus pi, on the other side. I'm talking about just trying to simulate this, represent it, whatever. And that discontinuous jump is called a kinematic singularity. It's bad. It does bad things to us. It means we can't just write down nice, clean ODEs. And I have to write this down as like a hybrid system or do other weird stuff that I don't like. So so what we want to do is that messes us up in our integrator, right? I can't write that down as a nice ODE. If I try to, the Jacobian mapping omega into phi dot is going to have a singularity at pi because of that jump, right? It's not differentiable. So I want to get rid of the jump. So I'm going to play a little geometry trick. I'm going to take this. So this is, again, all of this is actually happening up a dimension, right? So this is a ball in R3, not a disk in R2, blah, blah, blah. Keep that in mind, but you can visualize this all kind of this way. So what I'm going to do is I'm going to take that disk that's in the plane. I'm going to stretch it up out of the plane into a hemisphere. Okay, so I'm going to now, the picture is, I've got my disk, and I've sort of like stretched it up into this hemisphere now, right? And let's see, it looks kind of like this. Good. So what I'm going to do next, so this is the same thing. I just kind of stretched it up like this, right? What I'm going to do now is I'm going to make a copy of that disk, that hemisphere, and I'm going to take it, turn it around, and glue it on underneath. So where I had that, the one hemisphere, now I've got two hemispheres, glue them together. And when I glue them together, I'm going to flip it around such that this plus pi on the copy lands up with the minus pi on the new copy, so that I can keep going onto the southern hemisphere. So I get rid of the jump. Where I would have had to jump, now I just keep cruising onto the southern hemisphere copy. Does that make sense? Everyone get that? I take this thing, I flip it over, I make a copy, and now I make sure that the points where I would have had to jump line up on the new copy. So I'll write that down. Make a copy, rotate it, glue it on underneath to form a sphere. Now, instead of having to jump, we can just continue smoothly onto the sun of the hemisphere. Okay, does that make sense to everybody? So we just made quaternions from axis angle vectors. That's what you do. So now we have a nice smooth ODE, but we had to jump up a dimension, right? And we had to do this copying and gluing trick. So there's, we can write this down. We'll do the next time. I think this is, we're actually at time now. And this is like the key mental picture to have. And it explains just about everything there is to know about quaternions and all the weird quirks and stuff. Okay, thanks everybody. Yeah.